So he's saying iodate 5 ions, which are these ones. These are my reactants, right? And bromide ions. So my reactants are, I'm looking for iodate 5 ions reacting with Br minus 1 ions. And I'm going to see what's going to happen when the reaction happens. And it's acidified as well. And he's asking whether the reaction is feasible, and we have to explain. He didn't tell us to actually make the equation. So for bromine, there's only one equation in the data booklet. So it's Br2 plus 2 electrons in equilibrium with 2 Br minus 1. And I think the value or the E naught for that is, it's probably 1.07 volts. TK, make sure you have one data booklet open with you. So tell me, who's going to gain electrons, who's going to lose electrons in this equation? Like, which one gains electrons? Higher potential, lower potential?
The higher potential gains electrons.
Okay, so higher potential is going to go in the forward direction, and the lower potential is going to lose electrons, right? This is the part where oxidation happens. Lower potential loses electrons, and higher potential gains electrons. That's the part where reduction is going to happen or take place. And we can make an overall equation. Uh, uh, if I want to make an overall equation, I need to make the number of electrons gained and lost equal. So that means this has to be multiplied by 2, and that has to be multiplied by 5. So we can do the multiplication. That this one has to be multiplied by 5. So that would give me 10 electrons and 10 Br minus 1 ions. And this one has to be multiplied by 2. So this would become 12, and this one would become 10 electrons, and this one, the half would no longer be there, and it would be 6 H2Os. So we can construct the overall equation, which is not really needed in this case, but just for practice. So my reactants are 10 Br minus 1, and my products over here, my reactant in the other equation are 2IO3 minus 1 and 12H plus 1. The electrons are going to get cancelled out. What are the products? The products in the first one are, you've got the product is Br2, 5 Br2. And the product in the second one is I2 plus 6 water molecules. Those are the products. So is this reaction feasible or not? Now, the first thing is, he was asking for Br minus 1 and IO3 minus 1 acidified reacting. They are going to react. That's what we figured out. But how would you explain this? You would explain it using, because they didn't ask you to make the equation, so you're going to explain it using the E naught cell. The E naught cell is higher potential minus oxidation potential, or the more correct way is the reduction E naught minus the oxidation E naught. So who's gaining electrons? It's 1.19 volts. And who is losing electrons? It's the other one, 1.07 volts. And that gives you a positive value, which would be what, 0.12 volts. So in the explanation, it's a 1 mark explanation. The only thing that you were supposed to write was, you don't even have to mention these equations. You'll just go in the data booklet. You'll figure out the E naught cell. Like, this is the reduction, this is the oxidation, and the E naught cell is coming out to be positive. It's coming out to, I say, it's coming out to be greater than 0. So it's coming out to be greater than 0. That's why the reaction is feasible. So that's your explanation. Now, I'm just, for the sake of clarity, I'm just going to do another question about feasibility of reaction. I'm going to discuss a reaction. How would you do the same thing if the reaction wasn't feasible? Like, if you have if they had told us that, if they had already made us a reaction, like they've told us that you had Na plus 1 and Cl minus 1, and there's a reaction, and it's 2 Na plus 1 and 2 Cl minus 1, and it's producing 2 sodiums and a Cl2 gas molecule, right? And they're asking, is this reaction going to happen or not? So in this case, how would you explain that this reaction is going to happen or not going to happen? By just looking at it, it's probably not going to happen, because this is normal NaCl. It's Na plus 1 and Cl minus 1. We know it doesn't really react. We know that the sodium ions don't like to change into sodium atoms. So we kind of know that this reaction is not going to happen. But how would you explain this? The way you're going to explain this is again using the E naught cell. So this is, I'm doing the same thing for a reaction that's not feasible. In my data booklet, I have an equation where Na has only one equation, which is Na plus 1 in equilibrium with Na. And the E naught for that one is minus 2.71 volts. In the data booklet, Cl2 also has just one equation where it's in equilibrium with 2Cl minus 1, and the value is 1.36 volts. I said, now if I just go by if I try to construct the equation, the higher potential always gains electrons, the lower potential always loses electrons. So, I mean, that's going to come out to be feasible, but I have to look at the equation. Like, in which direction is the equation moving? The Na plus 1 is changing into Na. So the Na plus 1 is the one that's gaining electrons, right? According to the equation. And the Cl minus 1 is changing into Cl2. So the Cl minus 1 is changing into Cl2. So that's the one that's losing electrons. So this is your reduction happening. And this part over here is where your oxidation is happening. So I'm not going to decide myself. I'm just following what the equation is doing. I've chosen the direction according to the equation that they've given us. Now I'm going to try and calculate the E naught cell. The E naught cell is reduction potential, which over here is minus 2.71, minus the oxidation potential, which over here is 1.36. And that gives me minus 3.97 volts, I think, which is extremely negative. What that indicates is that what you're doing over here is completely wrong. The reactions, minus means the reactions are going to happen in the opposite direction. And that obviously makes sense because this one was the higher potential. It's supposed to gain electrons. I mean, it should go in the forward direction. And this one is your lower potential. It's the one that's supposed to lose electrons. It's supposed to go in the backward direction. So what you're doing over here is completely wrong. That's not the way the reaction is going to happen. Is this point clear?
Yes, sir.
Yes, sir.
So if E naught cell comes out to be less than 0, then that means the reaction is not feasible. Okay, Lubena, Shafaq, is this clear?
Yes, sir.
So sometimes just remember this. Sometimes they'll give you a reaction, and they would have made a wrong reaction, and they would ask you to figure out whether that reaction is feasible or not. So you just follow what's happening in the reaction, and you just try and calculate the E naught cell according to that. Because I mean, you obviously know that the higher potential is the one that's supposed to gain electrons. So I mean, you should know that whatever's happening here is completely wrong. That's not the direction in which the reaction should happen. As the next one, we've got extraction of aluminium oxide by electrolysis, and it's dissolved in cryolite. In this process, he's saying the half equation for the reaction at the anode is shown. If you know about aluminium oxide electrolysis, what happens at the cathode? Use this half equation to write the ionic equation for the electrolysis of Al2O3. So what we have done so far is we know that this is what's happening. What's happening at anode, right? It doesn't even remember what happens at cathode. Like which ion gets attracted to the negative cathode, and it's molten, so there is no water. Aluminium oxide has which two ions? It has Al3 plus and it has O2 minus. So Al3 plus ions are the ones that are going to get attracted to cathode, where they're going to get reduced, where they're going to gain electrons to form aluminium. Is this clear? Yes or no? Is this clear?
Yes, sir.
So the only thing left is you have to make the overall equation, because he's saying write the full ionic equation for the electrolysis of Al2O3. So you just add up the two equations. But before you do that, you have to make the number of electrons lost and the number of electrons gained equal. And for that, what you would have to do is you would have to multiply it by the first one by 3, So it's going to become 6 electrons, and the second one by 2. So this would become 6, and this would become 2. So the electrons are now equal, and they're going to get cancelled out. And your ionic equation, add up the left side, it's going to be 2Al plus 3. At the top, it's 3O minus 2. And you've got 3 carbons. And in your products, you have 3 carbon monoxides plus 2Al. So that's your full ionic equation for this particular reaction. Next is you've got he's saying calculate the mass of aluminium that is formed. Now we know that aluminium is formed when aluminium 3 plus get reduced. They gain 3 electrons to form aluminium. We just wrote that above. So what we need now is we're doing electrolysis, and he's passing a current of 3 for 3 hours, and the current has a value of 3.5 times 10 power 5 amperes. Now using Q is equal to I into T, current into time. Current is 3.5 times 10 to the power 5 amperes, and you're going to multiply it by 3 hours, which is 3 into 60 minutes into 60 seconds. And if we do all of that, does anyone have a calculator? What value do you get?
53 million.
53 million.
63.
63?
63 million.
So that's 6 zeros, right? So you found the charge, right? I'm hoping that's the right charge. So you found the charge. Now, since you have the charge now, it's one thing that we studied just recently. That was Faraday constant. I told you what's the Faraday constant. The Faraday constant is the charge on 1 mole of electrons. We know that 1 mole of electrons, they carry a charge of 96,500 coulombs. This was the last thing, and I told you about the Faraday constant. This was the ratio that was the one that was the only important ratio. That 1 mole of electrons, they have a charge of 96,500 coulombs. So if you've got 63 million coulombs, so how many moles of electrons are actually flowing through the circuit? That would be 6.3 times 10 power 6, and it's going to be divided by 96,500. What do we get?
662.8.
662.8.
652.
652.8.
Yeah.
So you're getting 652.8 moles of electrons, right? That's kind of a pretty big number. That's I mean, it looks fine. You're supposed to get a big number, yes.
Sir, I don't think the answer that you got above for like Q is equal to IT is correct. Because the answer that I'm getting is 37 I'll put into significant figures 1 second. Yeah, it's 3.7 into 10 to power 9 if I put into significant figures.
3.7 into
3.78 into 10 to the power 9. That's the final answer I'm getting if I put into significant figures.
Just one second. Let me. Actually, that's I can't use this calculator for. Can you read, Abdullah? Can you recheck?
Yeah. Sorry. It was 65.2. Yeah. Sorry.
This was 65.2.
Yeah.
Wait, the answer for this one is not correct.
The moles of the electrons.
65.2. Let's try and do this over here. Just 1 second. Let me. 3.5 times 10 power 5. So that's 3. So that's 1, 2, 3, 4, 5. That's 3.5 into 10 power 5. Multiplied by 3, multiplied by 60, multiplied by another 60. Right. So Abdullah, we get this, right? Shavak, you're getting this, right?
Yeah.
So it's and let's so I think we all are, and then this is going to be divided by 96,500. So we're going to divide that by 96,500, and I get 39,170, or we can write 39,171 moles. 39,171 moles, right? So we got 39,171 moles, right? TK,
Yeah.
is this the correct one, right? And
Yeah.
this one has to be, you now have to find the moles of aluminium. You found the moles of electrons that are flowing through the circuit. Now you have to find the moles of aluminium. That's going to be divided by 3. So divide the same thing by 3. And if we do that, what do we get? We got 13,057 moles. And we have to find, he's asking for the mass of aluminium. So the mass would be multiplied by the AR, which is 27. And what do you get? You get, so you get 352 dot 538. 538 grams, right? Is this clear?
So give me what is 539 or
That
538?
539. The technical, I didn't see this. So it's going to be written as, if you round it off, it's going to be 539.
Because I put it as 539, so I wanted to make sure it's correct.
So it's going to be 539. I'm also going to tell you about the technical details about these. I think I haven't discussed this with you. How accurate, how many significant figures is the time given in? That's 2, right?
Yeah.
And how many significant figures is the current given in? That's also 2, right? So the significant figures, they represent accuracy. Like, you know that it's 3.5. You just don't know what's after that. You don't know whether it's 3.50 or whether it's 3.51 or whether it's 3.512. So significant figures, they represent accuracy. So you're only accurate up to this point, up to the second significant figure. Is this idea clear?
Yes, sir.
As a similarly, 3.0 means that you just have an accuracy up till the first decimal place or the second significant figure. You don't know what's after that. You don't know whether it's 3.00 or whether it's 3.01 or 3.08. So I mean, whatever device you're using to measure it, it just doesn't give you that information. So your accuracy is only limited till the second significant figure. So your values that you're taking to do all this math, right? It's the first one is accurate up to 2 significant figures. This one is also accurate up to 2 significant figures. Now your answer is pretty accurate. It's accurate up to, like, it's got a lot of decimal places in it, right? So can you get a more accurate answer if your original values are not accurate? I mean, that's not possible. So if your starting values are accurate up to 2 significant figures, your final answer would also be accurate up to 2 significant figures. So you would have to round it off, because all the numbers that you're getting after that, there's a question mark on that. You're not sure what those numbers are. Is this idea clear?
Yes.
Yeah.
Okay. So always remember that I mean, they would probably be accepting answers, but this one would be the best way to actually write an answer. And we can also just quickly, it's March 20, just one second, 9701 and March 20, and it was, I think, let me just quickly open the market scheme just to check the significant figures. MS42. Usually they're not very strict with significant figures. So this one is 35, right? Just a second. So we can't. It's it's a big paper. Just one second. What's the question number? No, we don't. Question number 2. Yep. You can check over here that the answer that they gave you was 3.5 times 10 power 5. So they did accept the third significant figure, but the accepted form was just the second. Like you can write it in standard or the original form, but nothing is after 5. Is that clear?
Yes, sir.
So just be careful. They're not usually very strict with this, but you might end up losing marks for this. Sometimes you do actually, but it depends on the marking scheme. Like if they're awarding marks for that or not. Anyway, so the next one, leave that. That's not electrolysis. That's inorganic. We can move to the next question, which is this one. You've got your standard. So again, remember, keep this in mind. Whatever calculations that you do, this is accurate up to 3 significant figures. Your answer cannot exceed that accuracy. Even if you get lots of decimal places, you're not sure what's after this number. So any number that comes after the third significant figure that has an uncertainty in it, and you can't write that. As anyways, define the term standard electrode potential. So what's the standard electrode potential? It's the potential difference. I mean, you had an electrode and so it's the potential difference of a standard electrode compared to what? But the better way to write this should be it's a potential difference between a standard electrode and what? Who do you measure the potential differences with? TK, you measure it against a standard hydrogen electrode. That's your reference point. So you can write that it's the potential difference of a standard electrode compared to a standard hydrogen electrode, or between a standard electrode and a standard hydrogen electrode, measured under standard conditions. And you can mention the conditions as well, just to be on the safe side.
You mentioned like the standard conditions that are there.
How many? Just to be on the safe side, you can mention those.
Oh, okay.
1 atm, and if it's a solution, then it should be 1 mole per dm cube. Then you're being asked fully labeled diagram of the apparatus that would be used to measure the standard cell potential of the AU3+, an AU electrode, and the nitric acid NO electrode. So there are 2 electrodes, and both of these electrodes are not given in the data booklet. Like you can open the data booklet, and these electrodes are not going. I mean, the AU is definitely not there. So in A there is no AU, so AU is not there. So it could be so you just have to draw them. Now AU is a metal. So remember so I'm just going to quickly draw a rough diagram. AU is a metal, and so that's 1 electrode, and here's the other electrode is going to be, and the 2 electrodes would be connected with. So in the middle, there's going to be a voltmeter. So that's V. This is your AU electrode. And in the solution, there's going to be, in the solution, there's going to be AU +1 ions. And over here, there's NO gas. Whenever you have a gas electrode, it's always a gas jar. So there's going to be NO gas. And in the solution, there's going to be nitric acid. So these are your two electrodes. You've got an AU3 plus, sorry, AU3 plus. This should be AU3 plus. One thing is missing. What's that one thing?
The salt bridge.
Salt bridge.
Okay, so there's going to be a salt bridge. You can draw a salt bridge over there and label everything. Include all necessary chemicals and so write voltmeter. I mean, this is obviously AU3 plus NO. What would the electrode over here be made up of?
Cathode. Platinum. Yeah.
Platinum. Okay, it's going to be made from platinum. It's going to be a platinum electrode. That's going to be the label. This is the salt bridge. And just to be on the safe side, mention the conditions. Like the NO gas would be at 1 atmosphere pressure. The nitric acid should be having a concentration of 1 mole per dm cube. The AU3 plus over here should be 1 mole per dm cube. So mention these conditions. Just 1 minute for the azan. Just wait a few seconds for the azan. As I said, quickly now, same electrochemical cell. They gave you the electrode reactions, right? So who gains electrons? I mean, this is the AU3 plus electrode. You've got both things over here. The other one was the NO gas with nitric acid, so that's H plus 1, NO3 minus 1. So this is this electrode. We can ignore the middle one. That's I don't think there was any chlorine anywhere. So that one has nothing to do with our electrochemical cell. So he's asking for the equation. So higher potential gains electrons, and your lower potential loses electrons, and the electrons are already balanced, so you don't have to multiply with anything. The first reactant is AU3 plus, And the reactants in the second equation are NO and 2H2O, right? And the products in the first one are AU solid, and the product in the second one is NO3 minus. I mean, you can write the states NO3 minus 1 plus 4H plus 1, right? So that's the reaction that's happening, that's going on. The middle one had nothing to do. They gave that one. I don't know where that one is being used. He's asking you to calculate the E0 cell. So it's reduction potential minus oxidation potential. That would give you 1.50 volts minus 0.96 volts. And that gives you what? 0.54?
Yeah,
TK.
0.54.
So you're getting 0.54. Now, next one. Now, this one is so that equation over here, this one over here, was probably given for this part. He's saying gold can be oxidized by a mixture of concentrated hydrochloric. That's where the Cl lines are coming from. So gold can be oxidized. So there's gold oxidized. He wants it to lose electrons, right? So there's a reaction that's happening where gold loses electrons, right? And he's saying by a mixture of concentrated hydrochloric acid. So that happens when you've got HCl, which is concentrated, and concentrated nitric acid. So there's nitric acid that's also very, very concentrated. So gold can lose electrons, and that mixture HCl and nitric acid, he's saying that it's known as aqua regia, which is, so concentrated hydrochloric acid is 12 mole per dm cube, and the other one is 16 mole per dm cube. So that's 16 or 12 times greater in concentration compared to your standard conditions. So explain why aqua regia is able to dissolve gold. In your answer, state and explain what effect the use of concentrated hydrochloric acid have on E0 values for equations 2 and 3. So remember, so go back, and now we have to deal with concentrated hydrochloric acid and concentrated nitric acid. And remember, he wants an explanation. He wants gold to dissolve, right? He wants it to lose electrons. It should lose electrons either this way or, and over here gold is also losing electrons, right? Now if I have concentrated nitric acid, so he's talking about equation number 2 and 3. I think he specifically mentioned equations 2 and 3. So I think the first equation has too high a potential. I mean, the potential is pretty high for the first one. That's never going to lose electrons because higher potentials always gain electrons. So my bet is on the second equation. So tell me, where would the equilibrium shift if the nitric acid has high concentration? Forward or backward? क्या होगा? Anyone? Aruba, Shafak, Lubena?
Backward.
If nitric acid has very high concentration, the equilibrium is going to shift forward, right?
Move backward.
Forward.
I'm not sure.
If nitric acid has higher concentration, the equilibrium is going to try and decrease the concentration of nitric
okay.
acid. I mean, forget the potential. I'm just saying that there's this equilibrium isolated. If nitric acid has a higher concentration, the equilibrium is going to shift forward, right?
Yeah, okay.
And when it shifts forward, the potential increases. So let's say the potential increases to 1.20 volts, right? Because we did this, that these equilibriums, they can move forward or backward. When they move forward, the potential increases. I mean, this is just a hypothetical value, just to show you that the potential increases. On the other hand, the hydrochloric acid is also very concentrated, so that means Cl minus 1 is very concentrated. If Cl minus 1 is concentrated, then this equilibrium over here shifts backwards. And if it shifts backwards, more electrons are going to be produced and the potential is going to decrease. So let's say that it becomes 0.80 volts, hypothetically speaking. Is this clear?
Yeah, it is.
Yeah.
Achha, now will gold dissolve or not? I've just talked about equilibriums moving forward and backward. Now will gold dissolve or not? So who's the highest? Who's the higher potential now? It's 1.2 volts, right? So the higher potential
Yes.
always gains electrons, right? I mean, compared to the two, this one is the higher potential, so it's going to gain electrons. And who's the lower potential? It's this one. This one has the lowest potential now, and it's going to lose electrons. So gold is going to form ions now. Is this clear?
Yes.
Yes, sir.
ठीक है. In the original state, this was the higher potential, and this was actually the lower potential. But by making the Cl minus one more concentrated, you shifted the equilibrium in the backward direction. When you did that, the equilibrium value decreased. The E naught value decreased. And by taking a very strong concentration of nitric acid, the equilibrium shifted in the forward direction, and that increased the potential of this one. So this became the higher one, it started gaining electrons. This became the lower one, it started to lose electrons. And you can combine the two to make the equation where gold is now dissolving. Is this clear?
Yeah.
चलिए, let's continue with this tomorrow now, ठीक है? Okay, everyone, take care. Allah Hafiz.